I will briefly explain the idea of complex velocity based on an example, a simple example. For any analytic function, the derivative of the complex function omega with respect to z will give us a complex velocity. If we look very closely at the derivative of omega with respect to z, which we defined in the previous slides, you will see that it will give us a relationship, and the expression to the right, if you look at it very closely, you will see that it is an expression of velocity. One of them, in fact, the partial derivative of tau with respect to y is velocity along the x-axis, whereas partial derivative of phi with respect to y is the velocity in the y-axis. So this equation could be replaced by u minus iv. And this one is called complex velocity. It's known as the complex velocity. Well, this derivative omega with respect to z can be regarded as a complex velocity, the real part being equal to the x component and the imaginary part the negative of the y component of the velocity, velocity v being the main vector. So this is the relationship. You have both u and v. Given the function omega, you can determine u and v directly. So the absolute value of the complex velocity, if you take the absolute value of this, you will get the magnitude of the complex velocity, and that is nothing but the speed at a given point. Now, provided that the function omega fz is known, the equation of the complex velocity provides a ready means of determining the velocity at any point on the flow pattern in the z plane, and also we can determine the stagnation points in the flow by equating this derivative with respect to z to 0. I have here a very simple example to demonstrate how to apply this idea of complex velocity to determine the velocity at a point for a given analytic function, a complex function omega, which is 2z squared. We are to determine the magnitude and direction of the velocity at the point 3, 2, meaning 3 plus 2i in the complex. So I take the derivative of omega with respect to z, I get 4z. Then this must be equal to u minus iv according to our definition, and z is a point, known points at 3, 2. I can replace the value of z in this expression. It becomes 3 plus 2i times 4. Then further simplification will give us 12 plus 8i equals u minus iv. Now looking at this equation very closely, we find that u is 12, the magnitude of the velocity in the x direction is 12, that in the y direction is negative 8. This means that we have a velocity along x, velocity along y, given the given direction. The resultant of the velocity has a magnitude of 14.4, and it has an orientation, as you can see, of 34 degree 54 minutes and clockwise direction. So we have determined the velocity and magnitude, the direction of the velocity, only we were given the complex function. So that's a good way of determining not only the streamlines, the potential lines, but the magnitude of the velocity at different points in the flow pattern. This is very important, because if you know the velocity at different points, you can draw the velocity distribution. Moreover, from known pressure at other points, you can possibly determine the pressure at an unknown point. Thereby you can determine the pressure distribution. For example, if the flow is past a certain solid object, then you can determine the pressure on that solid object, on the surface of that solid object, and this is a very useful utility to determine drag and lift forces associated with the flow. Well, we will see this, for example, flow past a circular cylinder. We will take that example and work out how to determine pressure at different points on the surface. For now, I thank you for your attention.